right. Hello, everyone. So, as usual, recap. Of what we have done yesterday. So, what we did was to, first of all, understand what enters in the energy momentum tensor. That's radiation. And in general, relativistic species. Then we have matter that is composed by baryons and is composed by dark matter particles. Okay? This will be non-relativistic, massive particles that weakly interact. It is. Let me try to put it closer. Better?
I mean, we can hear you, obviously.
Can you hear me? Yeah? Okay, good. Nice. Okay, well, thanks. Technical check done. Okay, right. So we have radiation or relativistic species, so photons and neutrinos in our case. Then we have matter that is composed by baryons and dark matter. And then we have a contribution that is responsible for the acceleration of the accelerated expansion of the universe, and that would be the cosmological constant. Having learned about the energy momentum tensor, we then specify the species, and we use the adiabatic condition to derive the evolution of the various species, right? So we derived an expression that goes with the density of the various guys with respect to A. So we know what is their evolution as the universe is expanding, and this function depends on the equation of state parameter of the given fluid. Okay? Right, this we have seen. Then we specified the metric, and we imposed all our symmetries, homogeneity, and isotropy that boil down to our Friedman, Lemaitre, Robertson, and Walker metric. And then we reshuffled in various ways so that you have a feeling of how it can look like also in a different way of expressing the same quantity, because you can find all of those expressions in the literature. And once we have these two ingredients, what we did, we plug both of the two into the Einstein's equation. So that's G mu nu plus lambda G mu nu equal to proportionality constant, and then our beloved energy momentum tensor, T mu nu, right? So we did that, and the bottom line, we found out two equations, one and equation 2 with the expressions that I gave you yesterday, and they are the Friedman equations. So Friedman equations are nothing but the solutions of the Einstein field equations once we impose this metric, homogeneity and isotropy. Nice. Then we worked out a little bit the Friedman equation number 2. We introduced new variables, new quantities that are of extreme usefulness in cosmology, among which we identified the critical density, which is the density for which the universe is flat, k equal to 0, where k is the parameter within the Friedman, Lemaitre, Robinson, and Walker metric that specifies the geometry of the universe, flat, hyperbolic, or spherical. And we also identified, using the Friedman equation number 2 that I gave you yesterday, a condition for which we can have omega equal to 1. So whenever the density contrast, which is defined as rho over rho critical, is equal to 1, is equivalent to k equal to 0. Okay? So that's a strict condition. And that's extremely helpful because it constrains the various quantities, because we have seen that omega is actually the sum of all various omegas, because it has the omega of matter, there is the omega plus the omega of the relativistic or species, plus the omega of the curvature. So we've seen also how we can define an omega density contrast associated to the curvature, as well as the omega. We can do the same also for the cosmological constant. So you see, we have all of these guys that have to play together to give you the final omega. if we now impose a constraint, flatness, omega k is 0, disappears, you see that these three are linked together. So we don't have anymore three independent parameters, but we have two parameters. Because if I change omega lambda, the sum of the other two must respond such that we have always one. And the same is true for all the other components. Okay? Now let's leave this guy free. And having introduced these quantities, our Friedman equation, boiled down with the Hubble parameter, or the Hubble function, better to say, which is defined as a dot over a. So it tells us about the acceleration, the velocity at which the universe is expanding. And that's given by a normalization constant. This is h naught, which is this quantity evaluated at now, okay? At redshift 0 now. Times we have all the other components that are coming out from here. So we are going to have omega radiation times the ratio at which the density is dropping, a to the power of minus 4, plus omega matter, that goes a to the power of minus 3, plus omega curvature, that goes as a to the power of minus 2, plus omega lambda, which is a constant, and therefore there is no a dependency. That's our Hubble function, which is just the Friedman, one of the two Friedman equations. That's what we did last time. Now we shall continue. And what we're going to do is to define distances. That sounds like something trivial, just use a stick or something. Not that straightforward in cosmology, as I'm going to show you. Cosmological distances. That's the topic I'm going to discuss now. So, as I'm going to show you, the distances depend on how we define them. Okay, and we have different ways of defining distances. I will start with the simplest, which is the proper distance. That is using photons as a distance measure. Okay? So we have our, for interval, ds squared, which is equal minus c to the power of t, t2 to the power of t, plus the x2. Okay? So that's the space interval. And that's the time one. And we know that for photons, this guy is equal to 0. For you see that we can isolate this dx. That's a distance in a three-dimensional space. We do that, and I will call it d, big D, p, as a proper distance. D stands for distance, and p for proper, but it's this guy here. Okay? And that's going to be equal to, well, we do the square root of this expression, and what just we define it as c dt. Right? We bring this guy on the other side. I have this the x0 that is this one, and then I just perform the square root, and I get this expression. Nothing complicated. Now what we can do, we can relate the t to, we need to relate the t to the expansion factor a, right? We want to find an expression of d given a certain a. So let's do that. And what I'm going to do is to find this relationship. So from dA, we can go, for example, to redshift, or from time, we can go to dA. So we can have an expression that relates all these quantities, dA, dz, dt, dA. They're all linked together. Let's start with the first one. And that's simple, because we have the definition of redshift that we have seen yesterday, which is this one. And we just perform a derivative of this quantity. So this gives us the A is equal to minus the Z divided 1 plus Z to the power of 2. As simple as that. Definition, derivative. for this expression, we can use the Hubble function, or the definition of the Hubble factor. This, where was it? Here, this H. So H is A dot over A, that's the definition. And then we can isolate A dot, which is what? dA with respect to the t, just find the derivative of A, which is equal to what? Well, that's A times H, right? A dot is this one is H multiplied by A, this one. And then we get the derivative. The t is equal to dA over A dot, which is equal to the A over A H of A. Now we have all the relationships, so we can go from dA to the Z, we can go from dt to dA, and then, of course, to dA, the Z, so they are all linked together, yeah? Where, sorry? Here? Plus.
Since you use the ds square equals to minus c plus blah blah blah.
Yes.
Is it because at the present the metric is flat?
No. So if I write it like that, it is just expressing the three-dimensional part of the four interval, and that's completely generic. A is hidden in here, okay? As well as curvature and all of that. This is just a way of compressing the information. So I'm saying we have the spatial component and the space component. Whatever is happening here is just a length, okay? Yes, exactly, yes. So A and K are inside here, are hidden. Okay. But whatever is happening there is a length to the power of 2. That's it. Okay, nice. So we have the relationship, and you see that now we have our dt that we can plug into here. And once we do that, we have an explicit expression, which is C d of A with respect to A h of A. Now, what is it going to be, the distance? Well, we have to make an integral. Okay, so using not this part minus this one, just a difference between two locations in the space-time, but we need to integrate with respect to dA. Why? Because as we make the measurement through the photons, so that's the length covered by the photon, that's the length covered by the photon in the dA time, or the dt time, that corresponds to a dA time, the universe expanded in the meanwhile. Okay, so we need to account for all the expansion that is occurring as the photon is traveling. When we perform the integral, we just get the integral. So that's the p, which is c over h naught. So now I'm expressing this guy with the full Hubble function. Integral of dA with respect to a e of A. Remember that this expression is just written as h naught E of A. That's what this big E is, okay? It's all of that guy here. And you see, they contain the curvature. You see, the curvature is here. And there is the dynamic, h naught. It contains A, right? It contains the dynamic nowadays, and you see A. There is everything is incorporated there. So this is our first definition. Proper distance. What's the meaning of this expression? Why is it called proper? Because this is done in that's it. It's proper. So it's a physical measure between the separation between two space-time intervals. Then we have the comoving distance. That's it here. Then we have the comoving distance. Which now is defined as dr, so it's a length, equal to c dt over a. What happens? Now the a factor, I took it out. Okay? With respect to this expression, where the dx contained the e, now I took it out. Do you see that? Okay, remember the Freeman-Lamette-Robertson-Walker had a term with, I don't know, spherical coordinates, for example, everything multiplied times e to the power of 2. Okay? So e was hidden here. Now I took it out. I extract it. And I bring it on the other side of the expression. So now what is this guy? That's the conformal time. So now I'm making an integral, not with respect to time, but with respect to the conformal time. And again, what I'm going to get, I have my dt, and I plug in exactly the same expression that I derived earlier. Where is it? dt, this one. I just plug it here. And what we get is c dA over e to the power of 2 a h of e. What's the difference? E to the power of 2. And there is only e. We now perform enter 4 is the interval is, we can write it like that. It's just the proper distance divided by a. If we make the integral, again trivial, we call it comoving distance. These are comoving coordinates. That's equal to c h0 integral of the a over a to the power of 2 e of a. What happens here? That guy had e stored in its definition, and basically is a physical quantity, is a physical coordinate. The universe expanded, that's the measure between this point and this point in coordinates that were sort of sensible to the expansion. Then what happens? We have this step, and we divide it with a. So we are sort of canceling the expansion. So these are coordinates that are something like, imagine a rubber band in which we draw lines, okay? What happens now if I expand this rubber band, if the universe is expanding? The bands are expanding, right? If I look at the absolute measure of the expansion that I imposed, is this one, is the proper one. Instead, if I just count the tick between the lines that I draw as 1, the coordinates, the comoving coordinates are the coordinates that move with the expansion, that are co-moving. And therefore, if a tick through the expansion from this size become larger, it always counts as one step. Okay? They are extremely useful because, for example, they're used to deal with horizons, as we're going to see, so it's very convenient to have this definition. And, for example, in embodied numerical simulations, where people basically simulate the universe, in which they are like dividing the distribution of matter in small regions, and then they let each region interact one another through gravity. And then they say, that's the gravity, the universe is expanding this way, move, compute stuff, okay? And then things are going to happen, and I'm going to show you that as well, okay? Anyway, a numerical brute force to compute everything, and these sort of computations are done in comoving coordinates. Why? Because you just have a grid which is not expanding, and numerically is easier to deal with something like this. Okay, convenience in that case. Nice. you are right. 2. No, that's A. That's like this. Oh, here is 2. Here is 2. Where? Here. That's all squared. So when you do the square root, you have h. Hmm? I mean, EA, you can define it like this. Okay, I was starting to fill back the factor of 2. Okay? I mean, in the end, this is the expression. You got it. I mean, the point is, you have this expression, and this one, and everything is starting with the A dot. Okay? A dot, and this gives you an H here. That's it. H, and there's no power of 2. So you have a E to the square root of E to the power of 2 is E. Maybe I'm not understanding the question. Maybe we can chat later about that. Okay. Then, that's, as you see, that's a distance that is relating to the speed of photons. Okay, the travel that a photon went through in a certain amount of time. Then we have other ways of measuring distances. For example, parallax, or for example, measuring objects for which we know the physical size, right? If you have a standard ruler, they are called. Let's take, for example, this stick. And from your eye, you can draw a line that arrives at the edges of this stick. You define a certain angle, right? If I come closer to you, this angle is growing. If I go away from you, the angle is getting smaller. Therefore, you understand, if we have a physical ruler, a standard ruler, something that a physical object for which we know the size, and there are such things out there, then we are able to determine the distance between this object and yourself. And when we do this sort of measurements, we speak about angular diameter distance. Just repeat the drawing here. So this would be, let's say, we have a certain area. We have a certain angle. And the distance is called the ang for angular. Good. Now we can make a relationship between the area given, or the area of this surface, so let's call it the A, and we define it to be equal to the solid angle that we are measuring. So the exercise before was in 1D. You can imagine the same thing done in 2D, right? Defining a surface. Then that's related to the solid angle times the distance. That's exactly, we are constructing a distance which is equivalent to what we would do in a flat geometry. That's it. Right. Then what we have? We have an expression for which we have the angular, which is equal to dA over the omega, so the solid angle, 1 over h. Okay? Take care that this is the omega is the solid angle. It's not, it has nothing to do with the cosmological parameters. Okay? Just stress that. So here I just isolated this term. Right. So you understand that everything depends on the ratio of these two quantities, which we can express. Because being a ratio, we can ask ourselves what is the ratio of a certain infinitesimal solid angle with respect to the entire sphere. Okay? And this is going to be equal to the ratio of an infinitesimal portion of the surface enclosing that sphere divided 4 pi e to the power of 2, and then the distance which is proper, sorry, which is the comoving one. So this ratio must be respected. Okay, nice. If we do that, at this point, you see, we have our dA over the t. So I just bring this guy on the other side. The 4 pi goes away. This guy goes on the other side. And what we obtain is the angular, which is A dc. There is the square root, power of 2 dc. So I linked definition of this area with the comoving quantity. That's the definition. If you want, this is a definition, or the definition I already gave it here. As a consequence, is a definition as well, is the angular diameter distance. How we measure distances through the measure of angles. Then we have another distance, which is extremely popular, which is the luminosity distance. What does it mean? Now we are not using angle to define distance, but we are using luminosities. Imagine I have a lamp for which I know exactly the emission. I know the flux, the absolute flux in emission. Yeah?
So sorry, does that not mean angular diameter is the same as proper distance?
Then you define it also. Whenever you have a proper and comoving distances, you always have the factor of A that scales the two. So that you can always relate it also to the other ones as well.
Okay, but like just because angular distance is A times dc and dc is dp over A, is the angular not just proper distance?
That's the definition as I gave you refers to the comoving one. Okay, you get a relationship between the two. Okay, where was I? The lamp. Okay, so we have our absolute lamp, okay? They are called standard, not standard ruler, but standard candles. And if you know exactly what is the luminosity of this car, of this light, imagine the light of a car, you know that if it's very bright, it's close to you. If it's further away, it's fainter, you know that the distance is larger. So that's how, for example, we measure distances using supernovae. That would be a supernova luminosity distance. That's an emission that scales, you know, the flux as we are going with distance scales with r to the power of -2. That's how the area is scaling, right? So the flux is decreasing. That's not the only luminosity distance that we have, because we have also other type of emissions in astrophysics, which are not only due to photons. For example, gravitational waves. Gravitational waves are sort of a gravitational radiation, and we use a luminosity distance which is equivalent. In this case, we don't speak about standard candles, because they're made in light, but we are talking about standard sirens, okay? Like, that's because the frequency that we perceived on the space-time oscillation of Earth are on the audible frequency range, okay? If it would be something vibrate with that frequency, we would hear it, okay? So they call it standard sirens. But the concept is the very same, just a flux of photon radiations or space-time distortions, the gravitational waves. That is the full analogy. Okay, right. Good. So, as I already mentioned, the word flux, everything starts from that. So just recall the relationship between the flux, which is the amount of energy per unit of time per unit of area, that is emitted by an object, a source. And that's related to the luminosity, which is what we measure, to this relationship And here we have the luminosity distance, okay? So you see, we use exactly the same formalism that we would use in this room, but we are not just using a standard Cartesian separation between us and the source, like these lamps, but we are using the angular luminosity distance that we are going to define. So what are the units of these objects? As I said, is the amount of energy emitted per unit of time, emitted per unit of surface, joule, seconds, meter squared. Then we have to account for the fact that the flux is also redshifted as the universe is expanding, right? That's an energy. The universe is expanding. The energy of the photons, as they are traveling in my direction, is going down. Therefore, a redshift dependency is going to pop up here. Redshift. So it's like the intrinsic energy of the source get weak, fainter and fainter. Or let's say get lower and lower, not fainter and fainter, go to lower energies. Then we have a special dilution, which is due to the fact that the further we go, the larger is the area that has to be covered by that amount of flux. And then we have another term which is related to time. And that comes from the fact that we have a delayed arrivals of the photons. Let's call it gamma, the photons. So redshift goes linearly with respect to A. Therefore, if I take two separations labeled with A, so I have this time, or this A and another A, A1 and A2, then we have the ratio between the two. Twice is this value, twice is the redshift between the two. Then we have this contribution. We are talking about areas, and therefore areas, remember that this A is stretching length, goes with the power of 2, because it's an area, power of 2. And then we have the time dilution, and we have seen that as well, if you recall the conformal time, it's given again with a linear factor that is related to the ratio between the two. We put everything together, and this gives us a proportionality between the two locations of a power of 4. 1 to 1, total 4. Okay, perfect. And having that, our definition for the luminosity distance is going to be E1 over E2 to the power of 2. And we call it the angular. A1 and A2. Why are the two related, luminosity and the angular one? We are talking about areas, right? And when we measure the flux of something, we have a source, let's say that is emitting isotropically, but this is not that important. The flux is going through is through this surface. And therefore, the amount of infinitesimal surface on that sphere is given by an angle. That's why you use angular diameter distances. That's the definition that we are going to use for the angular diameter distance. Okay? And that's the angular diameter distance between these two locations in the space-time. Once we have done that, we have definition of distances. We can as well define volumes. And again, volumes are again something not trivial. And are built on the concepts that we just defined. How do we define the volumes? Well, we go along the line of the angular diameter distance. With the difference that now we have one portion of a sphere, and then, so let's say that has a certain angular diameter distance, this one, between 0 and this location, and then we just define the p interval. So again, based on the proper distances. That's simple, right? We define the angular diameter distance that is related to angles. I use the solid angle, so let's stick to the solid angle. And I'm just multiplying, I'm going to multiply this distance times the p. Again, related everything to proper distances. The dp is going to be, again, definition, dA of E, the p, d of p. As simple as that. Okay? Really simple way of constructing quantities. And now if we plug in our expression for the proper distance, we are going to have d angular to the power of 2, which is a function of a, times the omega, times c dA over h naught e of e. Now writing in a slightly better way, this gives us a factor of 2 of a, and then we have c over h naught 0, the z over the omega. Okay, so what I did here now, expressing everything in terms of redshift, just to show you that you can have this relationship using the expression that we derived earlier. You see, we have the relationship dA to transform everything in the z. So I just plug it in here, and I get this expression 1 plus z e of a. That's proper. If I want a comoving volume, so this is called proper volume, if I want it comoving, then it's very simple, because our dV comoving of A is nothing but dV proper of A divided A to the power of 3, because that's our volume scale, power of 3. Now if you plug in, the Vp that we had earlier, what we obtain, and again, if I express it as a function of redshift, so I can as well re-express A in terms of redshift, what we obtain is 1 plus Z, the Vp of A, which is equal to C over H naught, 1 plus Z, power of 2, dA of A, sorry, of Z, because I changed the variable, and E of Z in the Z, the omega. Now, why are volumes relevant? Why are they interesting? That's because, for example, we are counting objects in the universe. Let's say that we have a population of objects. Say galaxies. Say galaxy clusters. Okay? Some object that is living out there in the universe. For example, galaxies or clusters. And we are counting them. So I count them n. I count them n in a certain redshift interval and on a certain solid angle. Right? I'm pointing the telescope in that direction within a certain area in the sky. This would be our solid angle. And along a certain distance along redshift. Remember that the Z is related to A, so it's also a measure of separation. How many I count? I count them a certain number, n. So that's expressed with a number density, and perhaps is a comoving density, times the what? I want the number density times a volume. Which one? That's comoving. Therefore, which volume I'm going to use? I'm going to use the comoving volume. Comoving density, comoving volume. You need to be consistent. And then again, the Z and the omega. We now use the definition of our volume. So we have our number density of the population, which might have a redshift dependent because the galaxies are evolving as a function of time, as well as galaxy clusters, right? They're not passive objects. Not they pop up like this and they stay like that. They form. They merge one with each other. Therefore, their number is changing as a function of time. And in the end, just to give you the full expression, we have this C H naught E of Z. We have this expression. Why is this relevant? Imagine you are an astrophysicist. You are not a cosmologist. Okay? Usually the two things are sort of entangled. But let's say that you don't care about the expansion of the universe, but you care about the properties of galaxies. And you want to constrain their physical evolution, so how many they form as a function of time, or how many they disappear as a function of time. What do you need to account for when you make your observation? The cosmology. So to know what is the physical evolution of your astrophysical object, you need to embed them in a known cosmology. Because otherwise you don't have a relationship with the time, you don't have a relationship with volumes. So you need to know your space-time to define volumes and evolution with respect to time, if you do astrophysics. Astrophysics. Say you're a cosmologist. I don't care about astrophysics. What I'm interested in, this part, right? Therefore, if this one is fixed, I know that because, for example, I know because the astrophysicist told me so, how galaxies are forming. Then this one is given because I know the physics of the astrophysical object. What do I constrain? The space-time geometry. I have a constraint on the cosmological parameter. Look, E of Z, E of Z, E. Right? Cosmology. One contribution is here, and the other contribution comes from the population of clusters. Of course, there are not cosmologies and astrophysics separate as human beings, as well as there's not a universe which is split into different things, but everything has to be measured at the same time. So whenever, let's say, you want to do state-of-the-art measurements, or you want to incorporate or your knowledge, or not knowledge about the universe, astrophysics and cosmology, you need to make a fit which is comprising the two. So you have the parameters about structure formation, how structures form in the universe, and the one of the geometry together. And then there you fit your data having all this set of parameters together. Toward the end of the lectures, when we will know everything, or at least everything that we need for that, I'm going to go a little bit more into details here. Now I just want you to get the concepts, astrophysics and cosmology, through volume. So just to stress the importance and the relevance of volumes. Good. Let me just conclude this topic with just final remarks. So if we go for angular distances, we are using standard rulers. And for example, are the oscillations of the cosmic microwave background. In the intro, I already showed you a plot in which we have a mode. I don't tell you now what is it, a power spectrum. I don't tell you what's that. We will see it. But in any case, whatever we have a function of scales, and we have a data point that are coming from, for example, from the Planck satellites. And then if we use the lambda CDM model, we find something like that. And how can we constrain lambda CDM to these oscillations that we see out there in the cosmic microwave background radiation? Because this guy is a standard ruler. Okay? We have a fluid, a plasma, which has sound waves that are propagating in it. If we know the properties of the plasma, we know what is the frequency at which these waves are propagating. Okay? If we know when this plasma froze, as it's going to froze, and I'm going to show you that, because there is a decoupling that is taking place between matter and radiation, we will see that. The bottom line is that we know where these sound waves stop to move. Yet they froze like this. So we have oscillations with a physical size that we know. Standard ruler, we can measure an angular diameter distance, cosmic microwave background. The same phenomenon is occurring not only on the photons of the cosmic microwave background, but then these fluctuations are sort of the evolution that follows is given by the imprint of these frozen fluctuations. Okay? There are regions that are more dense in the universe and others that are underdense. And the overdense can grow, and the underdense can deplete it by matter because the matter is flowing where there is more gravity, so to say, okay? Where the overdensity is larger through gravitational attraction. And therefore, this is going to affect, for example, the formation of galaxies. Because where regions are more dense in space, you get more galaxies formed. There is more stuff that can collapse together to form galaxies. In the underdense regions, there are less galaxies. And therefore, by observing at the density fluctuation of galaxies in the sky, we can have another measurement of this guy. We call, in this case, technically, they're called baryonic acoustic oscillations, or BAOs. Baryonic acoustic oscillations. And the measures that are done are not with these millimetric observatories, such as, for example, Planck, but are done through clustering measurements of galaxies. Clustering of galaxies, of clustering of galaxy clusters. We are going to see all of that. I'm just making another fast forward such that you understand the importance of this sort of measurements. It's not just academic to see, oh, what's that? No, these are the measurements that are at the core of the measure of the cosmological parameters. Then we have the luminosity distance. And of course, when we were talking about density of galaxies and of galaxy clusters, of course, the volumes are relevant, right? Going back to the luminosity distance, we have supernovae. Of type 1a. Not all supernovae are good, because there are different explosion mechanisms. So supernovae are exploding stars in the final stages of their life, and the type 1a are a standardizable candidate. So we can measure their life in terms of the luminosity that they emit, and given that, we know what is their flux. They are a standard candle. We can use them to define distances. We have Cepheids. And these are supernovae on extragalactic sky, distances, sorry. Meaning we are living in this galaxy, in the Milky Way, which is sitting here, and there are other galaxies. And boom, a supernova is exploding in this galaxy. We are measuring this distance. Boom, another supernova in another galaxy, and we measure the distance. Then we have Cepheids, and these are stars that are within our galaxy. So these are galactic measures in which cosmology is not that relevant because the distances are not so large. But now we can also measure Cepheids in other galaxies. And that's important because we need to tune the absolute value of the supernovae, right? So what we do, we use the luminosity of the Cepheids, which is very well known. We exactly know as they do. They are very boring objects in the sense that they are pulsating stars, and they get brighter, fainter, brighter, fainter. They are a ball of plasma, very well, very simple, actually. It's very well constrained, and we exactly know what is their flux. Also because what? Because if the distance is small, we can use parallaxes, angular diameter distances, to measure their physical distance. And the angular diameter distance is the simplest one, because it's just making a measure, closing one eye, and opening the other one. By the flipping of the position, we can see what is the distance. Of course, for the distance through angular diameter distances of the Cepheids, we don't use our eyes or two telescopes next one with each other, but we have the sun in the middle, we have the orbit of the Earth, we perform one observation of the same object once we are in this position, we wait, once we are in the other location, on the other side, we perform again the same measurement. So what we have our Cepheid, which is here, and we know what is the angle. Alpha, we know the distance. Okay? Therefore, these sets are the so-called ladder distance. Okay, that's our ladder, and step by step we can define distances up to a certain point. Once we have the calibration, we can go to the next distance, and so on and so forth. So we start with the Cepheids and the angular diameter and astrometry. So we are using the parallax. So we start with the parallax. We go further away, and we can measure the distance of this Cepheid. And this is a lamp. That's our standard candle. Then we can go further away and have another Cepheid. Maybe it's in another galaxy. But now we don't need anymore the parallax, and we cannot even use anymore the parallax because it's too far. The angle is too small. Okay, I can wait to be on the other side of our orbit of the Earth, but I cannot, the angle that I get, you understand, from this picture, if I go further and further away, the angle is getting smaller and smaller and smaller. Okay, this angle closes, and is not usable anymore. But I already know what is the luminosity, and therefore I use the luminosity distance. But I'm in another galaxy, and in that galaxy, pop, I have a supernova, boom, that goes, a star that dies, explodes a supernovae 1A, and then I can tune the luminosity. So I know what is the luminosity of the supernovae, the absolute luminosity. And they are much, much brighter than the Cepheids. What does it mean? They can now observe them very far away. For far away, where the Cepheids are unobservable because they are too faint, I still have supernovae that goes boom. And you see that with this cascade of measurements and recalibration, and each step, we can basically quantify the luminosity distance, for example, if we are, now I just took the example of the luminosity distance. So we have the luminosity distances that can calibrate it in steps. And the luminosity distance, as I said, depend on A, cosmological measurement. A depends on the cosmological parameters. Let's go for a summary. Because we are done with this kind of the first step of our lectures. We went through the Einstein field equations. We started even earlier by introducing general relativity. we saw the assumptions that are inside that theory. And that's important because one part of the research that is done nowadays is to probe the universe loosening the assumptions, therefore breaking the assumptions that are intrinsic of GR, okay? So it's important that you know where these assumptions are. Then we imposed our symmetries and all of that. We found out the expansion of our universe. So we know how the universe is expanding given general relativity. And now we are starting to link our theory to something that we can measure. We are linking to observations such that we can constrain these omegas. Because without the omegas, we don't know anything. We don't know if GR is able to represent the universe. We don't know that. We need to measure them and see if our model is fitting the data. So what we did today, we defined cosmological distances. So I introduced the proper distance, which is just defined as the distance traveled by a photon in a certain amount of time. And that's the definition. I showed you that you can express this quantity with respect to time, with respect to A, or with respect to redshift, just using these simple expressions. Then we move to another definition. That's the comoving distance, which is defined like that, and is nothing but that quantity divided A. So now I'm not making the measure with respect to time, but I'm making the measure, that's the time of the photons that are covered in conformal time. So you see the T over A is the conformal time. And that's a measure that is following the expansion of the universe. Remember, the rubber with a tick, one tick sets the unit 1. If I stretch, the tick gets larger, but still is unit 1. Okay, I'm stretching the unit as the universe is expanding, comoving distance. Then we define the angular diameter distances by linking it to a measure through angles, as we would do like in Cartesian coordinate, and this is a definition. We define this quantity such that this expression is true. And just by making arguments related to the ratio between solid angles and areas, we found out our definition, our explicit expression. Then we went to the luminosity distance, which is related to the flux of a certain source. The flux is defined like that. And in an expanding universe, so in this room will be just a Cartesian distance. In the universe, that is expanding dynamic and with the geometry that it has, we need to define a distance. And we define it by just looking how flux, time, and length are scaling in cosmology, given the Friedmann-Lemaitre-Robertson work that we have. These are the scaling. That's the factor that is relating to different separations. And of course, we are using the angular diameter distances because we have this, the separation, that is, this distance depends on the angles with which we have dilution of the photons given a fixed area, okay? The further we go away, the more the photons spread on an area which is larger and larger, the flux is going down, so angles. Then I define volumes, which are related to the angular diameter distance times a step in redshift or in A, which is given by the proper distance. Again, a definition that is given like that. And then we just build it up with the previous definitions, and we got our expression. The last thing that I mentioned to stress the importance of volumes is that cosmology is often measured in terms using astrophysical objects, such as galaxy clusters or galaxies. And if you have a population of those objects that is coming out from cosmic structure formation, and again, we are going to find out what is this quantity, okay? So in the lectures later on, we are going to see how we can use our theory to predict the number of galaxies, general dark matter halos, we are going to see that is forming as a function of redshift, as this is linked to the geometrical properties of the universe. And now astrophysics and cosmology are linked together. Then having all these distances, since we are always referring, when we want to do cosmological measurements, to standard rulers or standard candles, I gave you the way that is used to define or tune our candles, to define what is the absolute luminosity of our candles. So we start nearby, where it's just enough to close and open the eye, and that means by observing an object in different locations of the orbit of the Earth, such that we can have a measurement, and this gives us our angular diameter distance. That's clean. It's very clean measurement because it's just geometrical. There is not any assumption on the source. This could be me, could be you, could be a lamp, could be a supernova, could be whatever. It doesn't matter. It's purely geometrical. It's clean. With this parallax, we can measure the physical distance of some source, and then we realize, oh, we know what is their flux now. And now we can use these objects observed further away, where we cannot use anymore the parallax, to measure distances. And look, if we have a Cepheids, for example, one of the stars that we calibrated, and a supernovae, then, oh, I know the physical distance of the supernovae, I know what is the absolute luminosity of the supernova. I can use it even if they are further away, under the assumptions that they are the same across the history of the universe. Okay? That's an assumption that is many times sort of under the carpet, but there is that, because chemistry is evolving as the universe is expanding, so it is there. But nevertheless, that's what is done. So if we can go, therefore, to extragalactic scale. We start within the galaxy, we go to the next galaxies, and then to the galaxies further and further away. And that's how we do it. Then, about these sort of observations, in the last part of the lectures, we are going to detail. Okay, so you're going to see how things are done for real. Good. So we can have a break, and after the break, we are starting with horizons, cosmological horizons. Good. We can resume at 3:30.